Okay, we ended last time with defining two lines where x1 was 1 plus t, y1 was negative 2 plus 3t, and z1 was 4 minus t, and L2 was defined as 2s 3 plus s and negative 3 plus 4s. Okay, so what we want to do is we want to show that this is skew. These are skew lines. So again, we set the x values to be equal, the y values to be equal, and the z values z value here is 4 minus t and equal to negative 3 plus 4s. And I'm going to go ahead and solve this middle equation for s. And s is equal to negative 5 plus 3t. And then I'm going to plug that in. Let's call this equation 1, equation 2, equation 3. I'm going to plug that in into equation 1. So I have 1 plus t is equal to 2 times negative 5 plus 3t. So that 1 plus t is equal to negative 10 plus 6t. And so we have 5t is equal to 11. So t is 11 over 5. Now if t is 11 over 5, that means, well, s was a negative 5 plus 3t. So s is negative 5 plus 33 over 5, which is negative 25 plus 33 over 5. That's 8 over 5. So what we have to do is check the corresponding points. So when t is 11 over 5, so t is 11 over 5, what do we get here? x1 is 16 over 5. y1 is negative 2 plus, so negative 10 over 5 plus 33 over 5, which is 23 over 5. And z1 is 4 times 5 is 20, so 20 over 5 minus 11 over 5, that's 9 over 5. And with s, we plug in the 8 over 5 that we have here. So for s, we plug in 8/5, and let me just check the z value here. z2 is negative 3 plus 4 times 8 is 32, 32 over 5. So this is negative 15 over 5 plus 32 over 5, which is equal to 17 over 5. So note that these two values are not equal. So these are not equal. Although, if I had plugged in this into, if I just solve for x2, for example, 2 times 8 over 5 is 16 over 5. So the x values were the same. The y values here, let's see, 3, 15 plus 8 is 20. So the y values would have been the same as well. But then the z value turned out not to be the same. And the reason for that is because we used the first two equations, which were in x and y, to solve, but then the z value didn't end up being equal, which means they don't actually intersect there. So hence, because Z1 at 11/5 is different from Z2 at 8/5, the lines are skew. Because the only hope was that they intersected S equals 8/5 and T equals 11/5, but the Z values turned out not to work out. Okay, so that was the exercise, and that's pretty much at least the basic part about lines. We'll do a little more line stuff once we finish the part on planes. So the next part is all about planes. Now, we're going to ask the basic question. The basic question for planes is, well, first note that given any 3 points, and we have to assume that these 3 points are not collinear. They're all in the same line, and there's lots of planes that go through them. But if you're given any 3 points that are not collinear, there is a unique plane in R3 passing through them. So that's an important fact, and that can be visually seen as follows. If you have a point here, and a point here, and your coordinate system is something like this, then if you draw the triangle that connects these 3 dots and you fill in the surface of this, well, that's pretty much your triangle. It's pretty much your plane. You can think of it as like a slice of pizza. It looks kind of like that. But essentially, this now extends off in space in this direction. It extends off in space in this direction. It keeps going, right? You can think of it like a if you're taking a knife and sort of slicing along, everything that you slice along this direction would be included in the plane. So just extend out to infinity. So you can extend the triangle out to infinity in all directions. Okay, so that's the first fact. So our basic goal is, just like for a line, it was if we have 2 points, can we find the equation of the line? For a plane, it's given 3 non-collinear points. Can we find the equation of the plane? But just like with lines, it actually turns out to be a little simpler with a slightly different geometric approach, which is given what's called a normal vector. And I'll explain what that is in a second. Given a normal vector and a point P on the plane, we can uniquely define the equation of the plane. So how do we see that? So let's first say we have a point P here. And let's say the plane looked something like this. Okay, I'm just going to draw a plane. Let's say we had and this point P is x0, y0, z0. Let's take another point. Let's call it, so this is the point x, y, z. Let's take the vector that goes from P to this x, y, z. Okay, so this vector, we'll call it v. This vector v is actually x minus x naught, y minus y naught, z minus z naught, right? It's the vector v lies entirely on this plane. A normal vector is a vector that is orthogonal. So let's draw our normal vector here. Our normal vector, we'll call it n. N is orthogonal to the plane. Orthogonal to the plane. So for example, Just off to the side here, if I had just our XYZ coordinate system, and we take, say, the XY plane, which is right here, XY plane, the vector, we'll call it n tilde, which is 0, 0, 1, which is just the unit vector pointing up here. That vector is orthogonal to the entire xy plane. And there's, well, the direction of the orthogonal direction is unique. So given a plane, right, so this normal vector will either it's going to be pointing upward or it's going to be pointing downward. You could extend it with, in length to make it a longer vector, but the direction is either up, what's called an upward normal. So this is what's called an upward normal. This vector here, I'll call it n tilde 1, which is the vector which is the vector 0, 0, negative 1, or could be 0, 0, negative 2 for that matter. I'm just giving an example of one. That would be a downward pointing normal vector, downward normal. This is an upward normal vector. In a similar way, if you have a plane and you can kind of put your hand out and literally just take your pen and make it orthogonal to the plane, that's your normal direction. And notice that n here, so the important fact here is the normal vector is orthogonal to v for any xyz on the plane. This xyz was arbitrary. If I chose another point, let me choose a different color here for that. If I had another point xyz over here, n would be orthogonal to that as well. So we'd have a normal here, or this would also be 90 degrees. So what happens is we're actually able to derive the equation of the entire plane using this normal vector. So notice this is saying n dot x minus x naught, y minus y naught, z minus z naught. This is the vector v. N dot v, if they're orthogonal, n dot v is 0. This actually turns out to be the equation of the plane. So let's give n some coordinates. So let's say n is a vector a, b, c. Then this actually turns out the general equation is abc dot x minus x naught, y minus y naught, z minus z naught is equal to 0. So this is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. This is the equation of a plane given, so this is given a normal vector ABC and a point P, which is x0, y0, z0. Okay, so let's just do this basic version. So as an example, let's find the equation of the plane. Find the equation of the plane passing through the point 0, 0, 1, and with normal vector n is equal to say 0, 2, 2. Okay, well, this is our x naught, y naught, z naught. So given any x, y, z on the plane, we have that n dot x minus x naught, so x minus 0, y minus 0, z minus 1 is equal to 0, where n now is 0 to 2. So what do we get here? We get 0x plus 2y plus 2z minus 1 is equal to 0, or simply 2y plus 2z is equal to 1. Okay. In general, you'll always end up with something of the form ax plus by plus cz is equal to d. This is the general form for a plane, which you get from starting off with this guy right here. Start off with this. When you solve it all out, you'll end up with this, and where this d, a, b, c, d are constants. This is a constant right here. This is a constant value. Let's just see what this particular plane is fairly straightforward to draw. So let's actually try to draw it, or at least it's not terrible to draw. Our base point was 0, 0, 1, right? 0, 0, 1. I'm sorry, I made an algebraic error here. This should be 2z minus 2, because I forgot to distribute the 2, so it should equal 2. I guess this can actually reduce then to just x plus y, or y plus z is equal to 1. Y plus z is equal to 1. Okay, so our base point was 0, 0, 1, so we have a point right here. Our normal vector was 0, 2, 2. So from there, if you draw 0 and then 2 and then 2 more, so from there, if you draw the normal vector, you would get something like this. This is our normal vector. So then our plane is orthogonal to that. It's going to be something like this. So this is, that's our plane. And this plane is, essentially you can think of, actually, if you think of just a yz plane, here's y, here's z, we have y plus z equals 1, which is just this line right here, if we just think of it as a two-dimensional thing. And then we extend out in the x direction. We extend out out this way, just like we're extending out here. Okay, you extend out in this x direction. Okay, so let's leave you guys with an exercise here. So exercise, find the equation, and then what I'm going to do is I'm going to give you the procedure to do this, and we'll do it next time. Find the equation of the plane passing through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So let's call this P, Q, and R. And what I'm doing is I'm going to give you a procedure, because we have a point. What we need is a normal vector. So what we need is the normal vector. We have 3 points, more than enough points. They're not collinear. You can check that. We need the normal vector. So what we're going to do is we're going to take note that let's take V to be PQ, the vector going from P to Q. Let's take W to be the vector going from P to R. So let me draw the picture here. Here's P, here's the point P. Here's the point Q. Here's the point R. And PQ is this guy. PR is this guy. Notice that our essentially the triangle defines the plane. If I finish the triangle, that would define the plane. What we're going to do is you're going to take the cross product. So you're going to take our normal vector here is just going to be v cross w, where here's v, here's w. So when we take the cross product, it gives us something perpendicular to both vectors, right? That's what we saw in the cross product section. So this is going to be orthogonal to both v and w, and hence it's going to be orthogonal to the plane. Hence it's orthogonal to the plane containing the points p, q, and r. So your exercise is to go ahead and compute these two vectors, go ahead and find the normal vector, and then find the equation of the plane. Find the equation of this plane. And this is going to be the general procedure given any 3 points. And we will start the next video with this.